Hello, everyone. My name is Mark Scott. I'm an associate professor at Miami University in Oxford, Ohio. Today, I'm going to talk to you about photovoltaic technology. So this is the technology that takes light and converts it over to electricity. The talk is going to focus on these 5 points here. So we're going to examine the photovoltaic effect. This is the effect, like I said, where light is incident upon a semiconductor material. That incidence causes a reaction at the atomic level, which generates electricity. Now, there are different types of solar panels that actually perform this conversion process. We've got our traditional silicon. We'll look at mono and polysilicon. There's also thin film and multi-junction, which I'm only going to talk about very briefly, but we'll move on to some of the other topics like maximum power point tracking. So you have a non-linear IV characteristic for each solar panel, and we need some type of system that will actually track that IV characteristic so we can extract the maximum amount of power from a panel or an array. After we cover that information, we're going to look at a data sheet and go over how you can derive information that you need to do some type of design. We'll show you the NREL data, which again will further allow you to do your design of a system, and then we'll go through a mock example of how you would design a system. Finally, after that, we will look at a off-grid application that we did here at Miami, where we provided solar power for an irrigation system for one of our farms on campus. Now, when we start to think about solar power conversion, we really have two forms that we run up against. So the first form is the photovoltaic. Like I said, this is what we'll focus on today. But the second form is concentration solar. So this is a lot like other types of power generation where you have, say, coal or natural gas that you would burn. You would use that heat to generate steam, and then that steam would drive a turbine. Well, in this case, you're taking all the light and you're focusing it on this single point here where you would heat up molten salt, and then that molten salt in turn ends up heating up water, and then that water runs over to a turbine and the steam generates electricity. But here, what we're going to focus on is photovoltaic technology. And so what happens there is that we have light. It's incident upon these panels here, and that causes electrons to be generated. And if we close that circuit, the electron flows, and this is how we end up with electrical energy. There are multiple different applications that you can think of when we consider photovoltaics. They start at very small levels like toys, calculators. Sometimes you'll see street signs that are lit up along the highway using solar panels. As we move up a little bit higher, you can think about your own house, having a solar panel on top of it so that it would offset your electricity bills. Companies are looking at it to put it on tops of roofs that are on warehouses, data centers as a way to extract even more energy. And we're going up to several gigawatts where we're actually replacing and offsetting the fossil fuel-based energy sources for renewable energy sources. In this case, what we're showing here is a 2 gigawatt utility that's in the United Arab Emirates. This here has 400 million panels installed to generate that amount of power. Where we begin with all this, though, is our periodic table of elements. I've gone ahead and I've eliminated the lanthanides and actinides in here just to make it a little bit more clear. But other than that, this is basically the periodic table that you ran into in high school and college chemistry. And so what we're interested in here is specifically semiconductors. So we know that we have conductors, which are really good at transferring electrical energy as well as thermal energy. And then we have insulators, which are the opposite of that. They're not good at transferring electrical energy or heat. Semiconductors fall somewhere in between those two. And so what we're really interested in is how can we modify these semiconductor properties so that we can achieve photovoltaic power conversion. Now, what we're going to focus on today is specifically silicon-based solar cells. I'll talk a little bit about thin film cells, less than a slide, but what you should know is that those are based on primarily cadmium telluride. It's a very popular molecule. And in fact, First Solar, who's a large producer of solar panels in the US, that is what they use in their thin film technology. I'll show you a brief outline of a multi-junction solar cell, just the way it extracts energy from the spectrum. And then from there, we'll just start talking more about the nuts and bolts of these types of applications. So this here is a silicon atom that you would see in maybe your high school or your college chemistry class. You'll remember that we have these different orbitals here. And so this here would be our 1s orbital, and we would have our 2s, 2p orbitals. So these things are shells where the electrons are actually occupying spaces. So they're discrete energy bands. And what we're interested in particular with silicon is the fact that it has missing electrons from its p shell. In fact, it's missing 4 electrons. So we know that silicon has 14 electrons, and shown that here based on just the different band diagrams. And what we really need, or what we want, is that this shell, the 3p shell, to be entirely filled with electrons. And so this is where we're going to get what's referred to as covalent bonding. And so one silicon atom will join with 4 other silicon atoms, and it'll end up sharing those electrons there. And so that would populate its top band. And so this achieves this equilibrium that molecules really like, where all the bands are occupied with the maximum amount of electrons. And you can see we've gone ahead and we've illustrated that point here. Like I said, these are covalent bonds. We have 3 different types of bonds that I remember from my chemistry class. And so this is just due to the nature of the molecules actually sharing the electrons. Now, what we've drawn here is a silicon lattice, and this might be a bit confusing. I find it in particular confusing. It's not really an easy way for me to visualize it. So I would go ahead and just draw it like this. And what we've done is we've taken the 3D lattice, we've reduced it down to a 2-dimensional lattice. And this is showing, again, the covalent bonds that we have between the different atoms and how they're sharing electrons. And so this is what a lattice, we can imagine a lattice looks like for a silicon molecule, for all intents and purposes. Now, what we do in engineering, or when we're producing a photovoltaic cell, is it's a process called doping. And so when we're talking about doping, we're specifically introducing atoms into the lattice. So you can see here that we've replaced one silicon atom here with, typically this is boron. And so boron, it is in the group 3 type element. So it has 3 electrons. So what happens then is that the electron that was here, it kind of comes over here and wants to fill that bond up. And so that leaves what we're referring to as a hole here. Hole is simply a vacancy in that valence shell. And maybe you can think of like a set of billiard balls. So you pull one out of the rack and you have a hole there. And then you put the ball back in, you have a complete rack of billiard balls. Now, this is referred to as a p-type material. Likewise, we have an n-type material. And so for an n-type material, we can use something like phosphorus. Phosphorus has 5 electrons in its valence shell. And so you can see here we have a free electron. And that free electron is able to participate in the conduction process. So I've gone to this website, pveducation.org. I think it's a really good website to explain the basics of PV. If you want more information, I would encourage you to go there and check it out. Now, what we were talking about with doping is how we're going to deliberately introduce these atoms. And so this little cartoon here is showing N-type material. The red orbs that are bouncing around here, those are going to represent our electrons. The blue ones are going to represent holes. And so you can see there's a whole bunch of electrons bouncing around in this N-type material. You still have a couple holes just from a natural intrinsic operation of the cell or behavior of the molecules. And so we also have down here P-type material. And so we're going to show the holes in this case as blue orbs. And again, you've got a couple electrons that are bouncing around here, just the inherent behavior characteristic of the molecule itself. But this one is going to be primarily dominated by holes. The interesting behavior that we have is that when we combine these two materials together through manufacturing process, we can take an N-type material and we can marry it with a P-type material. And we're going to end up with this depletion region in here. And so what's going to happen is that the charge on one side is going to, electrons on one side are going to migrate over to the holes on one side and create this region here called the depletion region. This is basically a barrier that prevents any kind of movement between the two materials after an equilibrium is established. And we can see the photovoltaic effect. This is the way things look when there's no light. And so we've got this intrinsic behavior of electrons bouncing around over here, holes bouncing around here. You can see that we have still a couple elements moving through the depletion region, but the quantity here is very, very small relative to the holes that are over in the P-type material and the electrons that are in the N-type material. Now, if we go ahead and we apply some type of stimulus, you can see that the number of carriers really starts to increase. And what's really not being shown here is that this depletion region has shrunk or even in some cases been eliminated. And so that's creating a route for these electrons to move over. And so if we go ahead and we short the connection here from the P-type material to the N-type material, you can see that we now have electrons participating in the conduction process. And so this would represent just shorting or actually using our solar panel. So this is some of the theory behind how the whole photovoltaic process works. So like we had said, this was all about how we go ahead and dope these materials so that we can get them to get those type of properties where we have a hole over here and we have a free electron. And so this is the photovoltaic effect here. Again, we'll illustrate it in a different way. This is going to be representative of our valence shell, which we're going to go ahead and show over here as far as the electrons that are in the valence band. And then we have the conduction band here, which we're going to refer to or designate as EC. This here is going to be the band gap. And the band gap is the amount of energy that's required for an electron to be able to move up to the conduction band. And so what happens is that light is going to be incident upon one of these cells. And when that happens, we have a hole and electron being created, just like we showed on the previous slide. And then after that electron is up in the conduction band, it is free to participate in the conduction process. And then eventually what happens is that electron will settle back down, it will combine with the hole, and we'll have the electrons back in our valence shell. So this energy here, this is a hard requirement for the electrons to move from the valence shell to the conduction shell. And if that doesn't happen, then there is no process for photovoltaic operation. So this cartoon here does a really good job of illustrating that further. You can see that we have our photon coming in there. It's incident upon the semiconductor material. That has created the electron hole pair that we were talking about. And now the electric field that is established and completed through the connection from the N-type material to the P-type material is allowing the electron to move through the circuit. And after it's done moving through the circuit, what it's going to do is it will come back over to the hole, combined, and the process will end up repeating again, where we have that photon generating the electron hole pair, and then in the end, the hole pair ended up combining again, and so on. So I talked to you about the band gap and how that we have this property where we need a specific amount of energy for this whole conversion process to take place. So we have this spectrum here, which is basically what we see on Earth. And you can see that for a silicon atom, that only a part of this spectrum is actually being used for energy. That's this part here in red. The rest of the energy in the spectrum is not being used at all. And so this energy here that has the longer wavelengths, that just passes through the semiconductor material. It's not incident upon the semiconductor. It's not really causing any kind of interaction. As we go smaller and smaller into this range here, the ultraviolet range, what happens is we have a bunch of thermalization losses that occur because the energy is almost too much. And so that extra energy beyond the band gap ends up turning into lattice vibrations and excessive heat. So we're not able to extract as much energy from the cell as we could. We're not using the entire spectrum as much as we could. So what people have been using are multi-junction solar cells. And in this case, this is basically a sandwich of materials. And so we have these different types of solar cells that are combined together, where we would have, say, I'm not going to bother writing that in there. This would be the gallium indium phosphide, gallium indium arsenide, and germanium. And you can see we have different band gaps here. So now we're able to pick up larger areas of the spectrum and extract energy from that light. Now, multi-junction solar cells, they're used in applications where you need very high efficiency. And one of those applications is on the International Space Station. But as costs come down for these, this may be an application that we can think about using at a utility level or a residential level, but certainly due to cost, that's not possible today, but maybe sometime later in the future. And so these are our typical solar cells that we're going to have for any type of application that we'd want to do, something like a utility or residential, really where cost is a concern. And so you can see the efficiencies that we've listed here, 22.6% efficient for the thin film technology, and then either the monocrystalline being higher at 26.1 or the polycrystalline being 23.3. So these are the current efficiencies that are given by NREL as of June 2024. So these are very recent. And you can look at these links down here if you want to get more information about that data, or if it changes between the time that you watch the video and when I record it. So I think at this point, what I'm going to do is I'm going to stop, and then we'll break it up, and I'll come back in a few minutes and we'll have another video. So thank you. I'll talk to you in a few minutes.